we are going to determine packing fraction for FCC unit cell, face centered cubic unit cell, FCC. This is actually 3. Already we have completed simple cubic and body center cubic. Okay, now we are going to find the packing fraction for FCC. We all know that in FCC unit cell, okay, I am drawing the cubic unit cell here, cube. First I will draw a cube. Now, in FCC, all the corners are occupied by the particles or atoms. Then all the face centers are occupied. Top face center, okay, side face center, this side, then front, back and bottom. All the face centers are also occupied. Now, in this case, observe carefully. If you view from the, this is the edge length. Since it is a cube, all edge lengths are equal. If you view from the top, how it appears? It appears like this. That is, all the corner atoms are not touching each other, but the middle atom, the face center atom, it is touching the surface of all the corner atoms. So, if you take this corner atom as A, the center of this corner as A, and this corner as B, and this corner as C, if I join A, the centers A and C, listen, this is A, center of A, and this is center of C. So, if I join these, this is equal to R plus R plus R plus R. So, this is A, this is C. So, what is AC? AC is equal to 4 times the radius of the atom. Okay, I am just looking from the top. Okay, and it appears that the middle atom, the face center atom, touching the surfaces of the corner atoms. Therefore, if you draw a diagonal here, that diagonal AC should be equal to 4R. 4R. Now, I will take this triangle ABC. See, in triangle ABC, the angle at B is 90 degrees. So, it is a right angle triangle. So, we can use Pythagoras theorem, according to which AC square equal to AB square plus BC square. Okay, what is AB? AB is small a, edge length. What is BC? BC also edge length. It is also a square. And what is AC? AC is equal to 4R. So, 4R square is 16 into R square. So, 16 into R square plus A square is 2A square. Therefore, I can write 1 2s are 2, 8 2s are 16. Therefore, I can write A square equal to 8R square, or A is equal to square root of 8 into R, or it is equal to 2 root 2 into R. We can write like this. Okay, take down. So, you know very well, packing fraction is equal to volume occupied by the atoms in one unit cell divided by volume of the unit cell. Okay, so what is the volume occupied? It is nothing but rank. Rank means number of atom per unit cell into volume of one atom, 4 by 3 pi r cube, divided by volume of the unit cell. Since it is a cubic unit cell, volume should be A cube. Okay, take down. Then for FCC, rank, number of atom per unit cell is 4. So 4 into 4 by 3, pi value 22 by 7 into r cube, divided by A is 2 root 2 r. So I will write like this, 2 into 2 into 2, because A cube we should take, root 2 into root 2 into root 2, root 2, then r cube. This r cube cancels. Okay, then we can cancel some numbers here. So let me show you. So 2 2s are 4, 4. Then I can cancel these numbers. Let me write clearly like this: 4 by 3, 22 by 7. Okay, into this 2 can be written as 1 by 2. Here 2 by 1. If we bring it to my 1 by 2. So this is 1 by root 2. See, root 2 into root 2 is 2. So I can write directly 1 by 2 into 1 by root 2. Okay. Now we need to simplify this. So 2 2's are 4. 4 we can cancel. Okay. So we get some number here. Right. So what we get is around 0.74 it will come. Let me give you the exact value. 22 by 21 divided by root 2. Root 2 is 1.414. Yeah, it comes as 0.7408. Okay, you will get 0.7408 packing fraction. This is packing fraction. Percentage packing fraction means you have to multiply this by 100. So you will get 74.08 percentage. Take down. Which means 74% of the crystal is occupied, a unit cell is occupied. Remaining around 21.09892%, it is empty. Okay, take down. Packing fraction. Listen, as I told you before, diamond cubic crystal. One second. So packing fraction for simple hexagonal unit cell. Take down. Simple hexagonal unit cell. Packing fraction for simple hexagonal unit cell. Okay. How to calculate packing fraction for simple hexagonal unit cell? Listen. You know very well hexagonal unit cell. Let me draw the hexagonal unit cell now. Then we will continue the discussion. Yeah, this is the hexagonal unit cell. We'll connect this and this. Yeah, hexagonal unit cell. Okay. Listen, in hexagonal unit cell, all corners are occupied by atoms. All corners are occupied. We have already discussed this. All corners are occupied. Then the top face center, hexagonal face center, top face center, and the hexagonal bottom face center are also occupied. Then we have 3 atoms at the middle of the unit cell. Okay. Listen, actually this top face form one layer and the middle one forms the second layer and the bottom one forms the third layer. So there are 3 layers actually. Suppose if you take middle layer one atom, sorry, this is top layer atom, this is middle layer atom, and this is bottom layer atom. This is top layer, middle layer, bottom layer. Can anyone tell me what will be this length? It is nothing but height. What will be the height? See, hexagonal unit, simple hexagonal unit cell, the top face is something look like a layer of atoms. And the middle 3 atoms, they form another layer. And the bottom hexagonal face is another layer. So we have 3 layers. Suppose in each layer, the atoms, right, are touching each other like this, then what should be the height of the unit cell? Anyone? Can anyone tell me what's the height of the unit cell? So here, the height of this unit cell, right, see here we have 3 layers, right, top layer, middle layer and bottom layer. Suppose if all the 3 layer atoms, if they touch like this, if one atom sitting on the surface of another atom like that, then H should be equal to 4R. But in the actual crystal, the middle layer atoms are present, are or exist in the depressions of the bottom layer, and the top layer atoms are present at the depressions of the middle layer. Therefore, the height of the unit cell is not equal to 4r. It is actually the height of the unit cell should be less than 4r. Okay. So what is the value, exact value? We can actually derive, but here I have given the value without derivation. Right? What is the value? H is equal to, we expect the height should be 4r, but it is less than 4r. How many times less than 4r? Okay, it is square root of 2 by 3 times less than, times the 4r. Okay, take note. This is the height of the unit cell. Right? And what about the volume? Listen, sorry, what about the base area? See, the base is a perfect hexagon. I'm taking this base. The base is a perfect hexagon. For hexagon, listen, for hexagon, we can divide an hexagon into 3 equivalent triangles, right? You can make it into 3 equilateral triangles, right? And area of each triangle is root 3 by 4 into a square. So we have 6 triangles like this. So 6 into root 3 by 4 into a square, where a is the edge length. A is equal to edge length here. So this is the base area. This is equal to base area. You know very well, base area into height will give you volume. So what is the volume of the unit cell? Volume of simple hexagonal unit cell. I'll write, okay, SH. SH means simple hexagonal unit cell is equal to, right, base area into height. Into height of the unit cell. What is the base area? We found out it is 6 into root 3 by 4 a square, and height of the unit cell h, which is equal to 4r into square root of 2 by 3. This is the volume, right? Now what is A? Actually, see, here we have one atom, here we have one atom. This is A, this is A. These atoms are touching each other. Okay, so this atom and this atom, they are touching each other. Therefore, this length is nothing but A, which is equal to 2r. So in this case, remember, in this case, A is equal to 2r. Substitute this A here. So you will get 6 into root 3 by 4 into A value is 2r. So A square is 4r square into 4r into square root of 2 by 3. So root 3 and this root 3 cancel. 1 4 1 4 we can cancel. So what we get here is 6 into 4, 24. R square into r is r cube, and here we have root 2. So 24 into root 2 into r cube. This is the volume of the simple hexagonal unit cell. Okay, take down. So what is packing fraction? Packing fraction equal to volume occupied by atoms, which is nothing but rank of the unit cell. Rank means number of atom per unit cell, into volume of one atom, which is 4 by 3 pi r cube, divided by volume of the unit cell. Okay, volume of the unit cell we have found out 24 into root 2 into r cube. Okay, now what is the rank for simple hexagonal unit cell? It is 6. We have discussed this in the last class. You just refer. Then 4 by 3 pi is 22 by 7 into r cube divided by 24 into root 2 into r cube. This r cube cancel each other. 1 3s are 3, 2 3s are 6. Okay, so what we get here is, listen, this is 4 into 2, 8. So 8 into 22 by 7 into, this is 24 by 1. So I can write it as 1 by 24 if I bring it to multiplication, and this become 1 by root 2. Okay, so now we will simplify. 1 8s are 8, 3 8s are 24. Then, yeah. So you'll get 22 by 21 into 1 by root 2. Okay, we'll find out the value. 22 by 20. I think this will also come out as 74, right? 0.74. Let me do it. 22 by 21 divided by 1.414. Yes, I am getting the same answer, which is equal to 0.740889. It comes around 0.89. Let me take the value as such. This is the packing fraction for simple hexagonal unit cell, and percentage packing fraction is equal to 74.08. Take note. Yes, now you try to tell me what is the packing fraction for simple cubic, body center cubic, face center cubic, and simple hexagonal unit cell. Packing fraction. Yes, anyone? So the values of packing fraction for some of the important unit cells are given here. Okay, take note. What is the meaning for tetrahedral void and what is the meaning for octahedral void? Listen, suppose you place 3 atoms like this. 3 atoms or 3 molecules or 3 particles in general. You place 3 atoms like this. See, they are all balls. Just imagine like a ball. If you place 3 balls close like this, okay, you will get a depression here. Depression. Now I'll place an atom in the depression also. They are all similar atoms. Observe carefully. I have, first you take 3 balls and keep them closer. You will get a depression. In the depression you place another ball. If you join the centers of the all the balls, you take the center of this ball, and the above one, you connect them, you will get a tetrahedron. You will get a tetrahedron. Now there is a gap. There is a gap here between all the 4 balls. Between all the 4 balls there is a gap. That gap is called a tetrahedral void. That gap is called a tetrahedral void. Why is it a tetrahedral void? Because if you join the centers of all the 4 balls, you will get a tetrahedron. And the gap that is present is actually present in the middle of the tetrahedron, so it is called tetrahedral void. Okay, take note. In general, number of tetrahedral voids is equal to twice the number of atoms, twice the number of atoms per unit cell, or number of atoms in the crystal or in the unit cell. Number of atoms per unit cell, that's the meaning actually. Okay, or I can say this rank, number of atoms per unit cell. Okay, so to find number of tetrahedral voids, you just find number of atom per unit cell, multiply this by 2, you will get number of tetrahedral voids. Okay, it's very simple. Take note. Here, listen. Suppose I'll take
Sir,
yes, we'll do a problem here. Suppose I'll take an hexagonal primitive unit cell. Primitive means simple. So I have taken an hexagonal primitive unit cell, right? Can anyone tell me what is the rank of hexagonal primitive unit cell? Okay, so rank is equal to 6 here. Now, what is the number of tetrahedral voids? Number of tetrahedral voids is equal to 2 times the number of atoms. So 2 into 6 is 12. So in hexagonal, primitive hexagonal unit cell or hexagonal primitive unit cell, there are 6 atoms present in one unit cell, number of atoms per unit cell. Since there are 6 atoms, there should be 12 tetrahedral voids must exist. Okay, take note. There should be 12 tetrahedral.
Sir, அந்த rank மட்டும் கொஞ்சம் side.
Yeah. For listen, rank. Okay. Yeah. Just note down. For simple cubic, rank is 1. For BCC, rank is 2. For FCC unit cell, rank is 3. For primitive hexagonal, okay, I'll write like this: PH or simple hexagonal, whatever it is. For this, rank is 6, and for diamond cubic, I'm very sorry. Yes,
sir.
For diamond cubic, it is 8. Take 2. You try to
4,
do it.
sir.
Calculate. This is a very important one. Sometimes we expect questions, multiple choice questions from this particular concept. Okay, next. Okay, so the next one is about octahedral voids. Octahedral voids. What is octahedral void? It's very simple. Listen, I'll take 3 balls. I'll join them like this. Okay. Then I'll take another 3 balls and I'm going to place the balls in this manner. That is, see, I'm drawing with a different color now. I'll place one ball here. These 3 balls with the blue color, they form one layer, and in the above layer, I'm placing 3 balls like this. Observe carefully. We have 3 balls below and we have 3 balls above. Right? See what I did? I'll just draw separately and show you. Listen, I took 3 balls first, like this. Then I took another 3 balls. Let me show like this. 1, 2, and 3. This is layer 1. This is layer 2. Now you place the top layer, or you place this layer on this. If you place it, you will get structure like this. Now when you place like this, observe carefully. If you join the centers of the above 3 balls and centers of the below 3 balls, observe carefully, here balls means atoms. If you join the centers of the above 3 balls and below 3 balls, okay, and if you connect all the centers, okay, you will get octahedron shape. Right? By this appearance, you may not view that shape effectively, but you will get octahedron. And the gap present at the center, this is actually called the octahedral void. Octahedral void. Okay, take note. Number of octahedral voids in an unit cell. Number of octahedral voids is equal to number of atoms in one unit cell. Take note. Number of octahedral voids is equal to rank of the unit cell. Take note. See, number of tetrahedral voids is equal to, it is equal to 2 times rank. Rank means number of atom per unit cell. Now here, according to this formula, rank is equal to number of octahedral voids. So number of tetrahedral voids is equal to 2 times number of octahedral voids. We can write like this: octahedral voids. Take note. Density of a
Last page also.
So the next important one is density of crystal. You know very well, density is an intensive property. Therefore, to find density, you need not take the entire crystal. Okay, since it is intensive property, you can take one unit cell and find out the density that is equal to density of crystal, because it is intrinsic property, right? So how to find density? Density is nothing but mass by volume. What is the mass of atom present in one unit cell? It's nothing but rank of the unit cell. Rank will give you number of atom in one unit cell into atomic mass. Okay, I am assuming that the crystal made up of atoms. Okay, so atomic mass or the lattice points, right, are occupied by atoms. So rank into atomic mass, right? Listen, we usually put atomic mass in gram per mole. For 1 mole of atom we'll put the mass, right? Atomic mass means mass of 1 mole of atoms. But we want mass for 1 atom, so divide this value by Avogadro number. Avogadro number. So atomic mass by Avogadro number will give you mass of 1 atom into rank will give you mass in 1 unit cell divided by volume of the unit cell. Suppose if you take a unit cell as cube, then A cube will give you the density. Take note. So this is the formula we use to calculate density of the crystal. Take note. So carefully. Density depends on rank. As rank increases, density also increases. Therefore, density of simple cubic, density of BCC and density of FCC, if you compare, okay, compared to simple cubic, in BCC, see, simple cubic rank is 1, BCC rank is 2, FCC rank is 4. As rank increases, density will increase. Okay, take. This is a general idea. It's a general idea. Keeping other things constant. Okay, suppose, see what I'm trying to say here, this is very important point. Suppose I'll take a particular atoms. I'll take a particular atom. Assume that this atom forms both simple cubic, BCC and FCC under different conditions. Okay, let us assume in this manner. Suppose I have some atoms. Those atoms form simple cubic, BCC and FCC under different conditions. In this case, if you compare their density, since the atoms are same, the densities are not equal. Okay, density depends on the crystal structure. So for FCC, density will be very, very high. Okay, take note. See, iron atoms, right, can form BCC as well as FCC under different temperatures. Okay, so in BCC, iron atom form BCC. In FCC also, iron atoms are occupying the lattice points. But densities of these crystals are not same. Though iron atoms form BCC as well as FCC, right, the densities are not same because rank for BCC is 2, rank for FCC is 4. Okay, therefore FCC has little higher density compared to BCC. Okay, take note. This is often called as ideal density, expected density. But due to some defect, you may not get the expected density. The density may be lesser than the expected value. Okay, take note. What is mean by crystal planes? Take note. Crystal planes. Crystal planes. Suppose I'll take a cubic unit cell. Actually, this need not be cubic, but just for understanding purpose, I'm taking cubic. Right? I'll fix this corner as origin. Then you take this axis as x-axis, this as y, and this as z-axis. Okay. Now this unit cell cuts the x-axis, right, at some distance, and this is what we called as x-intercept. This is called x-intercept. right? And it cuts the y-axis at a particular point, and this length is called that y-intercept, and this is z-intercept. Okay, so now what I'm going to do, you take some plane, right, in an unit cell and try to find out what are the intercepts present. Once you know intercepts, then you can find the corresponding Miller indices for the planes. Observe carefully. We represent crystal planes, right? Crystal planes are represented okay, using Miller indices, that is HKL. We represent like this. We represent crystal planes using the curved brackets, and inside the curved bracket you just write HKL. These are all called Miller indices. Okay, take note. What is the method to find Miller indices for a crystal plane? Okay, what are the method? First, you find out. These are the steps you should follow. Steps number 1. First, you find out the intercepts. Meaning you take some plane, or for a given plane, you find out what is the x-intercept, what is the y-intercept, and what is the z-intercept. Okay, so find out the x-intercept, right? Usually x-intercepts, if you take this unit length as A, and this length as B, and this length as C, the x-intercept, y-intercept, or z-intercepts are given in terms of this x, A and B or C. Okay, right? So first you find out the x, y, and z intercepts. It is given in terms of A for x-intercept, in terms of B for y-intercept, and in terms of C for z-intercepts. Okay, then after finding the intercepts, right, then take the reciprocal of those intercepts. Reciprocal of the coefficients of the intercepts. What I'm trying to say, we'll discuss everything as we go along, right? Suppose let me take L1 into A as x-intercept, L2 into B as y-intercept, and L3 into C as z-intercept of the intercepts made by the plane. Now see the coefficients. The coefficient of A here is L1, coefficient of B here is L2, coefficient of C here is L3. Okay, these coefficients, you take the reciprocal of those coefficients. Reciprocal 1 by L1, 1 by L2, 1 by L3. So first identify the intercepts, then take the reciprocal for the coefficients. Okay, reciprocal for the coefficient. Then what to do? Clear the fractions. Clear fractions. Okay, but very important, but do not simplify. You are not supposed to simplify. Okay, whatever value you get, you keep the value as such. You should not simplify. Okay, then after clearing fraction, then you will get values, okay, H, K, L, and write them in a curved bracket without commas. This is what we call the Miller indices for a given plane. Okay, take note. Now let me show a plane here, just for understanding purpose.
Sir, last page one.
Yes, how to proceed. See, listen. I'll show. I'll take one example using simple cube. Let me draw a simple cube here. Simple cube. Now I'll keep a plane here. So where I'm going to keep the plane, listen. So this is the origin, and this is the x-axis, this is the y, and this is the z-axis. Now I'm going to take a plane here. Listen, my plane is here. I'll take this plane. I'm taking this surface as plane. Okay. What is the Miller indices for this plane? Miller indices for this plane. Listen, very simple. See, this plane is parallel to x-axis. This plane is parallel to x-axis. Therefore, so I'm finding intercepts. Listen. So what is the x-intercept? Since the plane is parallel to x-axis, x-intercept is infinity. Whenever a plane is parallel to any axis, then intercept for that axis should be infinity. What about y-intercept? See, this plane cuts the y-axis at unit length. So it cuts the y-axis at unit length. Let me put the length as 1. It cuts the y-axis at unit length, so you put 1. And this plane is also parallel to z-axis. Therefore, the intercept for z-axis is also infinity. Take note. Yeah, let me take the reciprocal of this. Reciprocal 1 by infinity. 1 by 1 is 1 only, and this is 1 by infinity. This is the reciprocal. Okay, and what is 1 by infinity? 1 by infinity is 0. Here 1, this 0. So 0, 1, 0 is this plane. So this is the Miller indices for the plane 0, 1, 0. Take note. In this plane, this is nothing but h value, and this is k value, and this is h l value, h k l values. Right? Take note. See, number 2, I'll take another plane in the same cube. Observe carefully, it's very important. So this is the x-axis, and this is y, and this is z, and this is the origin. Now, since you asked me whether all faces have same Miller indices or not, listen, suppose I'll take this plane. Okay, I'm taking the top surface as plane. Now, first of all, you find out the intercepts. Okay, let me do it here. Intercepts. Is the plane cuts x-axis anywhere? It is parallel to x-axis, am I right? This plane is parallel to x-axis. Therefore, intercept for x-axis is infinite. Is the plane cuts the y-axis? See, it is also parallel to y-axis. So, y-axis intercept also infinity. What about z? Yes, the plane cuts the z-axis in unit length. So, I'll put 1. Now, take the reciprocal. Reciprocal 1 by infinity, 1 by infinity, 1 by 1 is 1. Okay, and 1 by infinity is 0. This is 0, this 1. So, this plane is what we call as 0, 0, 1 plane. Okay, take note. Are the Miller indices same for this and this? Check it. See, now I have given a plane here. Find the Miller indices for that plane. Okay, yes, how to do that? Right? To find the Miller indices of this plane, what to do? See, this plane is passing through the origin here. Whenever plane passes through the origin, okay, what you have to do? You shift the origin from that place to the neighboring corner. So I just shifted to this place. Now, listen, for the same plane, see, this is the x-axis, this is plus y, and this should be minus y now. Minus y, and the above one plus z. Now, what are the intercepts, you tell me? Intercepts?
0, -1, 0.
Very good, sir. intercepts equal to, intercepts I'll find out, x-intercept, it is parallel to x-axis, so x-intercept is infinity. It cuts the y-axis in the minus direction, so it is -1 in the unit direction in the negative side. Then it is, see, I just shifted, now this is my z-axis, this is my z-axis. Now it is parallel to z also, so infinity. It cuts the y-axis only. It is parallel to x as well as z now. Okay, and take the reciprocal. Reciprocal 1 by infinity. This is 1 by 1 is 1 and 1 by infinity. 1 by infinity. Okay, and you know very well 1 by infinity is 0. -1 should be written as bar 1. Sir, observe carefully. -1 should be written as bar 1 and 1 by infinity is 0. Take note. This is the Miller indices for this plane. 0, bar 1, 0. Now I have given a plane here. Okay, the plane is actually passing in the diagonal direction inside the unit cell. It cuts the x-axis, it cuts the y-axis, it also cuts the z-axis in unit length. So how to find the Miller indices? Very simple. The first step is find the intercepts. Since this plane cuts the x, y, z at unit length, so x-intercept, let me take it as 1, y-intercept, let me take it as 1, and z-intercept 1. Take the reciprocal. Reciprocal of 1 is 1 only. Therefore, I am going to write the Miller indices directly, that 1, 1, 1. So this plane is called 1, 1, 1 plane. Okay, take them. See here, I have given a plane here. This plane cuts the x-axis at 1 by 2 length and cuts the y-axis in 1 by 2 and z-axis also 1 by 2. Okay, with respect to the unit length, right? Now you find out Miller indices for this plane. Listen, how to do this. See, first you find out the intercepts. Intercepts are given here as 1 by 2 along x-axis, 1 by 2 along y-axis, and 1 by 2 along z-axis. Now take the reciprocal. Take the reciprocal. We'll get 2, 2, 2. There is no need to find fractions and all. It is already in whole number. So the plane is represented as 2, 2, 2 plane. Okay, this plane is called 2, 2, 2 plane. Right? Take that. The question is, find the Miller indices for this plane, which is present in a diagonal direction. Okay? Yes, fine. So, what are the intercepts? Let me write here. Intercepts. Okay? Along x-axis 1 unit. Along y-axis 1 unit. Along z-axis it is parallel, so intercepts is infinity. Now take the reciprocal. 1 by 1. 1 by 1 is 1 only, and 1 by infinity. Okay, 1 by 1 is 1, 1 by 1 is 1, 1 by infinity is 0. So this plane is called 1, 1, 0 plane. Now I'll give like this. See, say some axis, crystallographic axis are given like this. Okay, this is my x-axis, this is the origin. This x, this is y, and this is z. Right, now I didn't mention the unit cell is cubic or not. It may be of any type. Now listen, these are all unit length. These are all unit length along x-axis. And these are all unit length along y-axis. And these are unit length along z-axis. Observe carefully. Suppose I'll give a plane like this. I'll give a plane like this. What is the Miller indices for this plane? What is the Miller indices for this plane? This is the question. So what to do? Listen, it's very simple. Along x-axis, see, intercept, this is 1 unit length. This is 2, 3, 4. Along x-axis, the intercept, let me write here. along x-axis intercept is, suppose for unit intercept if it is a, then it is 4a along x-axis. Along y-axis, if the unit length is b, here I have 1, 2, 3, 4, so 4b. If the unit length along z is c, then this is 1c, 2, 3, so you have 3c. I have taken the intercepts. Now take the coefficients. The coefficients are 4, 4, 3, and this is what we call as Weiss indices. It is sometimes called as Weiss indices. Take them, Weiss. Okay, Weiss indices nothing but the coefficients of the intercepts. Now take the reciprocal. 1 by 4, 1 by 4, 1 by 3. Now we have fractions. So clear the fraction. How to clear? Just multiply by the LCM. So we have 4 and 3, so LCM 12. Multiply throughout by 12. So what we get? 3, 3, 4. So remove the commas. So this plane is called 3, 3, 3, 3, 4 plane.